So in the treatment of MIMO systems, up till now, we have always assumed that you have the knowledge of the channel side information at both the transmitting end and the receiving end. So CSIT, which is the channel side information at the transmitting end, and the channel side information at the receiving end is assumed always. So you can have the channel side information at both the transmitting end and the receiving end. That would mean you would have higher complexity. You need to estimate the channel at the either at the receiving end or and then feed it back to the transmitting end so that the transmitter side also has the channel side information. Or what you can do is that you can have pilots transmitted by the receiving end, and then you can estimate the channel at the transmitting side. So that is called the receiver side pilot transmission. And then assuming that the receiver also can have the knowledge of can estimate the channel, so you have the channel side information at both the transmitting end and at the receiving end. So the question is, can you achieve something if you don't have the channel side information at the transmitting end? So can we achieve diversity gain if we don't have channel side information at transmitter end? So that is the main question. So that question, so let's try to look at this question. So suppose you have two transmitting antennas and you don't have the channel side information at the transmitting end. So, and you suppose we are talking about diversity gain here and not the multiplexing gain here for the moment. So let's suppose that you have this signal S1 of t that is transmitted from the first antenna. And if you want to achieve some diversity gain, then that would be equal to S2 of t. Let's call this S of t. You have the signal S of t that would be transmitted by uh, both of these channels. And let's suppose that so suppose you are talking about multiple input and single output system. Right? So you have two transmitting antennas and one receiving antenna. So if that is the case, whether or not you would be able to get some diversity gain if you do not have channel side information at the transmitting end. So if say H1 and H2 are the channel gains, then what would be the received signal, right? So your received signal R of t would be equals to so you would put one half of the energy in the channel 1 and one half of the energy in the channel 2. That would be equals to 1 over root 2 times H1 times S of t plus 1 over root 2 times H2 times S of t. And that would mean that your received signal would be equals to 1 over root 2 times H1 plus H2 times S of t. So that means that suppose your H1 and H2, right? So for the sake of analysis, or whether or not it is giving us up gains, let's suppose that H1 and H2 are both uh, normally distributed with mean of 0 and a variance of 1. So they are standard normal random variables. So if H1 and H2 are standard normal random variables, then this would mean that H1 plus H2 would have a distribution that would still be 0 mean, but the variance would increase from 1 to 2, right? Because you have two standard and normal random variables added together, their variance would add them together. But that would be h1 plus h2. What about 1 over root 2 times h1 plus h2? So 1 over root 2 times h1 and h1 plus h2 would have a distribution, would still have a mean of 0 and a variance of 1 over root 2 squared times 2. That means it would still have a variance of 1 over root 2 times h1 plus h2 would be a random variable which would have a mean of 0 and a variance of 1, because 1 over root 2 squared would be 1 over 2 times 2 would give you 1. So that means what? That means that if you do not have channel side information at the transmitting end, the signal that is received has the same distribution as it would have been received by a size case. That means if you do not have any if you're not using any multiple antennas. So this means same distribution as size. This means no diversity gain. And the reason you do not have any diversity gain is, of course, because you don't have any channel side information at the transmitting end. You cannot vary the power that is transmitted from antenna 1 and antenna 2, for example. And you cannot, not only you can uh, vary the power or the transmit power in the two dimensions, you cannot also co-phase your signals. Remember, the gain typically you get is because of the co-phasing, um, uh, using the maximal ratio combining, so that you can co-phase your signals, and that would get you an array gain as well as a diversity gain. And because you would not be able to co-phase your signals, nor you can adapt your power in the different channels, so you would get no diversity gain whatsoever if you do not have the channel side information at the transmitting end. But if you're using only a one time slot for the transmission. So there is, however, a way to get something out of a MIMO channel, even if you um, do not have the channel side information at the transmitting end. And that is the solution to this problem. The solution is use both space and time dimensions. If you're only using the spatial dimension and you are transmitting both of your signals in the same time slot, you would not be able to get anything out of it. So if you however make use of the space as well as the time dimensions, you can still get some diversity gain even if you don't have any channel side information at the transmitting end. And the very basic the very basic setup is what is called the Alamouti scheme. So Alamouti scheme, Alamouti is of course the name of the inventor for this particular scheme. He used to work at Bell Labs, and the scheme works over both the spatial and the time dimensions. And for a very simple scenario, if you have two transmit antennas, the Alamouti scheme works over two time slots. So combined together, if you transmit the signal in a certain pattern and you do the signal processing over two time slots, then you would be able to get some diversity gain out of it, right? So, for example, you have this time slot 1 and you have this TX1, TX2. Okay, so you have two transmitting antennas and two time slots. So this is your time slot 1 And then you have this time slot 2, and again you have this tx1 and tx2. So what Alamouti proposed was that you can achieve some diversity gain by following this method. That during the time slot 1, you transmit signal S1 of t from transmitting antenna 1, and S2 of t another signal from the from the from the transmitting antenna 2 simultaneously. So you transmit S1 of t and S2 of t simultaneously during the time slot 1. And during the time slot 2, you transmit minus S2 conjugate of t from the transmitting antenna 1 and S1 of t from the S1 conjugate of t from transmitting antenna 1. So using this, you would be able to get something out of it. So let's see how this works. So in the time slot 1, you receive signal y would be uh, h1 times s1 plus h2 times s2. That is what you receive. And in the time slot 2, you receive signal y would, so you can call it y1. This y2 would be equals to h1 times minus s2, or minus h1 times s2 conjugate, plus h2 times s1 conjugate, right? And if you take the conjugate of this equation, so you can get y2 conjugate would be equals to minus h1 conjugate times s2 plus h2 conjugate times s1. And now you work with these two equations. So you have this equation that you received in time slot 1, and this equation that you received in time slot 2, and you did the complex conjugate of this thing. You have this. So if you combine them together, so um, let's take this y1 and y2 conjugate and put them together in a vector form. So that is your vector y. Let's call it vector y. That would be equals to, remember we are using these two boxed equation. So the channel coefficients that have been multiplied is h1, h2, and then remember the thing that is the channel that is being multiplied with s1 is h2 conjugate, and the channel gain that is multiplied with s2 is minus h1 conjugate. Plus, of course, we missed out on the noise, right? So of course, you would have noise terms here. You would have plus n1 plus n2, and because you're taking conjugate, so this would be plus n2 conjugate. So you would have n1 and n2 conjugate. So this is your received signal in the matrix form. So we would call this as a y vector. We would call this as HA, channel matrix. This would be your S vector, and this would be a noise vector. So you can see that your y vector is nothing but, so you can call it x because we have been using x. That would be equal to HA times x plus your noise vector. That is what you receive, right? And then you would be saying that how would this would give you some diversity gain. So you would need to do some signal processing for that to happen at the receiving end. So what you can notice is that if you have HA Hermitian times HA, if you want to compute this, what would this look like? So HA Hermitian would be equals to H1 conjugate times H2. You take the transpose and then you also take the complex conjugate. Then H2 conjugate here and minus H1. That would be your HA Hermitian. And if you multiply HA Hermitian with HA, you get a special matrix. So if you carry out this multiplication, you would see that what you receive is would have H1 mod squared plus H2 mod squared in the diagonals, and in the non-diagonals position you would have zeros. Okay? So in other words, you would be able to diagonalize your matrix by doing the simple signal processing. So this means your HA Hermitian times HA is nothing but H1 mod squared plus H2 mod squared times an identity matrix, right? Simply you can write H1 mod squared plus H2 mod squared times I2, where I2 is a 2 cross 2 identity matrix. So that is the property of the channel, and that is the property of the channel you can only get over the two time slots. So you have to assume that the channel would remain correlated over two time slots. So that is the assumption, right? And now using this property of the channel matrix, that HA Hermitian times HA would give you a diagonalized kind of a matrix. You can just receive. So remember, your received signal Y is nothing but HA times x plus n. Now let's say that you have this vector z, which is nothing but HA Hermitian times y. And if you carry out this, that would mean that you have HA Hermitian times HA times x plus HA Hermitian times a noise matrix. And that would mean that you have this HA Hermitian times HA is nothing but H1 mod squared plus H2 mod squared times I2 times x, right, plus HA Hermitian times n. So that would mean what? That would mean that your Z1 would be equals to H1 mod squared plus H2 mod squared times S1 plus N1 tilde, where N1 tilde would be the first element of this vector, HA Hermitian times n, and your Z2 would be nothing but H1 mod squared plus H2 mod squared times S2 plus N2 tilde, where this vector we are calling as N tilde vector. Okay? So you have these two elements, and you can see that what has happened here is that you are able to diagonalize your channel matrix. In other words, you are able to make uh, you are able to receive your signal over the two independently fading multi paths or paths, and hence you would get a diversity order of 2 here, right? So that is very important, that you, because of this diagonalization, you would get a diversity order of 2, and which was not possible if you do not have the channel side information and you don't make use of the spatial and the temporal, both of these dimensions. This, of course, is a simplistic scenario, right? And in this simplistic scenario, you have only you had only two transmitting antennas and you had only one receiving antenna. Of course, if you have empty cross, MR, number of transmitting antennas and receiving antennas respectively, then you can extend this concept to what is called the space-time block codes. And you have different kind of architectures of the space-time block codes. It was so simple at first that people thought that this would have been done, either it would have been done by someone else, or this is too good to be true. But as it turned out, that it was, although it was a simple technique, but it has a lot of merit, and it reduces the complexity at the transmitting end, and that gives you a diversity order of almost empty MR, right? If you have an empty MR transmitting antennas and receiving antennas, and uh, at a slight cost of the added complexity in terms of the signal processing you're talking about. So that is a very, very groundbreaking result that is now being implemented in a lot of practical applications as well. So that is the key thing, is that it was simple thing. It has now been used in these blast architectures are being used in a lot of practical applications as well. So one important thing that I want to comment here is about this noise vector. So this noise vector, H Hermitian times n, what would be the covariance matrix of this noise vector? So the covariance vector, so if you compute the covariance matrix expected value of n tilde Hermitian, uh, n tilde times n tilde Hermitian, what would be that? Right? So that would be equals to the expected value of HA Hermitian times the noise vector times HA Hermitian times the noise vector, and its Hermitian, right? And this you can write as expected value of HA Hermitian times this noise vector. Remember, AB whole transpose is B transpose times A transpose. So that you can write it as N Hermitian times HA Hermitian whole Hermitian, that would be HA. And hence you can write this matrix as HA Hermitian times expected value of N times N Hermitian, which was your original um, uh, covariance matrix of the noise, times HA. So that is important. So now this is equals to HA Hermitian times sigma squared times an identity matrix times HA. So this you can see is nothing but sigma squared. So I2 times HA would give you an HA. So this would be nothing but sigma squared times HA Hermitian times HA, and that would be equal to sigma squared times H1 H1 mod squared plus H2 mod squared times the identity matrix. So the important thing here is that your noise variance has also increased because of this signal processing that you have been using here. So if you want to compute what is the signal to noise ratio, gamma gamma 1 for the first branch, that would be equals to um, h1 mod squared plus h2 mod squared times, if you suppose that half of the symbol energy is given here, the whole of, so this is the gain, the eventual gain that you get after the processing, h1 mod squared plus h2 mod squared, square of that times the symbol energy. If you suppose that half of the energy is given to the first symbol, divided by your noise variance, h1 mod squared plus h2 mod squared times sigma squared, you can see that your signal to noise ratio would be equals to, this would cancel out this square, and then you would have h1 mod squared times es by 2 plus h2 mod squared times es by 2. In other words, um, um divided by sigma squared. So your signal to noise ratio here is equals to, so your signal to noise ratio of the first branch, signal to noise ratio of the second branch divided by 2. So, so this you can see this is nothing but 1/2 times your H1 mod squared times ES over sigma squared plus H2 mod squared ES for sigma squared. So your signal to noise ratio on each of these branches is nothing but 1/2 times the signal to noise ratio of the first branch plus the signal to noise ratio of the second branch. In other words, you don't have any increase in the signal to noise ratio whatsoever. That means you would not get any array gain whatsoever. So no array gain. Although you would get some diversity gain as explained. You would get some diversity gain, you would not get an array gain using the Alamouti scheme. Would that improve the performance? That is the question, of course. What does this mean in terms of performance? Right? So that would mean that, for example, if you have this, for example, if this is the performance of the maximal ratio combining, and say this is the performance with no diversity. Without diversity, you are really bad. With maximum ratio combining, you get a very good performance. Where would be the performance with Alamouti scheme? Remember, this is your signal to noise ratio. This is your bit error probability or symbol error probability here, right? So with the Alamouti scheme, so you would get a penalty of 3 dBs because you would not get any um, array gain, but you would get a diversity gain. That is more important. So you would get a 3 dB worse performance than maximum ratio combining with the Alamouti scheme. So that means much improved performance as compared to no diversity, and that too with no channel side information at the transmitting end. So that is the key advantage of the Alamouti scheme, that you can get a lot of diversity gain without having any channel side information at the transmitting end.